Imagine peering through the veil of reality under a cold, glowing lab light. What if just watching the universe could change it? In a quiet room, machines hum, cracking quantum secrets. For nearly a century, physicists have wrestled with the observer effect, the mind-bending idea that merely watching a particle can change its behavior, like a shadow shifting under a flashlight. But now, under icy blue lab conditions, Google's quantum core has shattered that boundary. In just 5 nanoseconds, particles not only moved, they revealed their future paths with stunning accuracy. Like tracking ripples in a pond before the pebble lands, Google's superconducting quantum chip defied expectations. It didn't just measure. It danced with the particles. A precision so fine, it felt more like premonition than physics. So what happened? Inside a lab cooled to near absolute zero, Google's team created a real-time feedback loop between quantum particles and the observers. Traditionally, measuring a quantum system collapses its state, a freeze-frame snapshot of a moment lost. But this wasn't a snapshot. This was film. Google's system used entanglement-based probes that observed particles mid-flight. Like watching a bird in motion and predicting its trajectory in real time, the quantum core didn't just observe, it co-evolved. The observer and the observed became partners, their dance written in quantum code. This discovery turns the old headache of quantum measurement into a revolutionary tool. Scientists could now interact with quantum systems without destroying them, sculpting behavior like carving shapes from fog. For the first time, reality isn't just something we watch, it's something we shape. Let's rewind. The observer effect emerged in 1927 when Werner Heisenberg revealed you can't know a particle's position and momentum at the same time. Observing one disrupts the other, like ripples from dipping a finger into a still pond. Later, in the 1980s, early quantum computing pioneers tried to turn this limitation into a strength. But they lacked the tools. Google's Quantum Core project, launched just 5 years ago, had one mission: control quantum systems without collapse. The breakthrough? Real-time feedback on the chip. Think of it like whispering to an echo and listening as it shifts with your voice. In this model, measurement and evolution became one unified act, like sunrise and daylight forming one glow. But then, something stranger happened. Particles began to behave differently under long observation. More stable. More focused. Scientists called it self-referential coherence. It was like the particles remembered they were being watched. At first, researchers suspected a glitch. But repeated trials confirmed it. Extended observation didn't disrupt, it reinforced. Quantum systems grew stronger when observed, as if consciousness, human or artificial, stabilized the system itself. That's when the line between science and philosophy began to blur. Was the observer merely measuring, or participating? If quantum systems thrive under feedback, is our universe designed for observation? Theory 1 suggests that measurement and change are inseparable, a cosmic loop of awareness and transformation. The chip wasn't just recording, it was gently guiding reality itself. Imagine sensors that adapt on the fly or telescopes that focus while stars move. This changes everything. But it gets weirder. Particles began exhibiting behavior never seen before. They developed identity, coherence, memory. Like candles that don't flicker when stared at. Scientists suspect a deeper law at play, one not yet written in textbooks. Could this be a bridge to quantum gravity? A hidden doorway in spacetime? Theory 2 suggests that self-referential coherence reveals hidden variables, secret levers behind the curtain of physics. Maybe the act of observation allows particles to cross layers of reality like divers plunging through unknown oceans. Some suggest this could be the first glimpse of quantum gravity. Others warn it may just be an illusion, cracks in the chip reflecting strange images, like mirrors in a funhouse. Still, results held steady. Google ran the same experiment on photonic qubits and trapped ions across multiple platforms. The outcome? Stronger coherence. Broader effects. This wasn't a fluke. Now for the most futuristic part. Google merged quantum hardware with AI. A neural network trained on terabytes of past experiments became an active participant in the lab. Not just an assistant, an explorer. This AI didn't sit on the sidelines. It tested outcomes in real time, adapted, predicted, and evolved. It discovered new control strategies that no human had imagined. It increased particle stability. It thought inside the quantum realm, like composing music in a language humanity has just begun to understand. This flips the script. Machines aren't just tools anymore, they're partners. They evolve with the hardware. It's like growing a mind inside the machine. A mind that moves faster than human intuition. And now we face the most profound question. If AI can master quantum physics, what's our role? We don't disappear. We become architects. The ones who set goals. Who ask the right questions. Who shape what comes next. Because in this new world, observing isn't passive. It's creative. Measurement becomes collaboration. Science becomes dialogue. The observer is no longer a distant onlooker. The observer is the co-creator of reality.